My name is Niki Tsiburaki. I am a PhD student of the University of Patras. Today I will present you a study entitled Random Vibration-Driven Prediction of Residual Fatigue Life and Strength of Thermoplastic Coupons, an Experimental and Numerical Approach. In short, the outline of this presentation is an introduction and the technological problem of estimation of the residual fatigue properties from model characteristics. After a short reference to the existing bibliography and the demonstration of material and experimental procedure, the flowchart of the used material methodology will be explained. The residual fatigue life and strength estimation through random vibration model characteristics will be described, and the main conclusions will be presented at the end. It is worldwide known that in the last decades, the aircraft composite content by weight is increasing and by now is up to 50%. At the same time, thermoplastics have attracted attention due to their advantages, such as recyclability, weldability, and enhanced impact performance. And although there are already adoption from the aircraft industry, more research of their fatigue behavior is needed to achieve a safe operation and smooth aircraft flight. In this context, the structural integrity and life of an aircraft is crucial, especially from which aspect is examined. Implementing experiments, developing numerical models, and taking advantage of the available material properties datasets and enriching them continuously provides a complete image of the aircraft state. Hypothesizing that there is a fatigue damage in an aircraft, sensors will record immediately response signals with appropriate methods. Existence, severity, and the location of damage can be estimated. Through regular structural integrity inspections and proper maintenance and high-level safety can be reassured, our remaining useful life estimation can be predicted. The general technological problem is the lack of prediction failure while an aircraft operation due to the difficulty and the complexity of the fatigue in composite materials and the estimation of the residual fatigue properties from model characteristics. It is very important to be clear what is missing from the existing bibliography. The model-based residual fatigue life prediction metrics have three main subcategories. Firstly, examining the natural frequencies and damping ratios behavior with increasing number of cycles. Secondly, examining the natural frequencies behavior using theoretical mathematical models to capture with more detail their exact experimental model response. And thirdly, a combination of methods, natural frequencies, SVM algorithms, and artificial neural networks to assess the residual fatigue properties. The two first methods combine model tests and empirical models attempting to investigate the problem, as the last one combine and compare different methods attempting to evaluate them. The gap on the present literature is the development of a general numerical methodology for predicting the residual fatigue life and strength of thermoplastic composite materials, considering progressive fatigue damage. The goal of this study is to explore the correlation between the progressive fatigue damage evolution and the model characteristics of thermoplastic coupons, and to establish a numerical predictive tool. In the present study, TAFC 1225 LM-Pike thermoplastic composite is used with causisotropic stacking sequence with a layup, as you can see here, and with 0.14 millimeter ply thickness of its ply. The coupon dimensions were in accordance with ACTM standards, as you can see here. A total of 28 coupons were tested in the experiments. Initial tensile tests and fatigue tests were conducted for material characterization. Additionally, interrupted fatigue tests were conducted, and every 10,000 cycles, the coupons were subjected to random vibration tests and ultrasonic C-scan immersion tests. From this test, model characteristics and damage index were determined. Furthermore, static tensile tests were carried out after fatigue loading to evaluate the residual strength of the coupons. Combining all the above results, an experimental assessment of residual fatigue life and strength is achieved. The interrupted fatigue tests were conducted in an MTS landmark machine with an 100 kilonewton load cell. The equipment for the random vibration test comprised a laser vibrometer, a controller, an NI 9230 acquisition card, speakers, and a personal computer. The excitation is acoustic, MATLAB-generated white noise, while the coupons were supported by a lasting charge simulating free boundary conditions. The excitation frequency was 6 kHz and the sampling frequency was 12.8 kHz. The probe used in the ultrasonic C-scan operates in a pulse echo mode. A probe frequency of 5 MHz and a gain of 10 dB were fixed for all tests. In such a study, uncertainty sources cannot be ignored. Here, coupons population, operational, environmental, and fatigue damage accumulation are present. The numerical methodology of residual fatigue life and strength assessment through random vibration responses is similar to the experimental one. First, static tensile model, which is validated from the initial static tensile test. Secondly, progressive fatigue damage model, which uses Hassin failure criteria, which is validated from the C-scan images on how the damage evolved. Thirdly, the random vibration model, which is validated from the experimental PSD weld spectrums. And fourthly, the second static tensile model after the fatigue loading, which is validated from the second series of static tensile tests. Below, a graphical illustration of numerical methodologies presented, and especially each numerical model separately, with aim the prediction of residual fatigue life and strength. At this point, the experimental damage index from C-scan images is explained. The lamination area is considered as the only damage here. For each fatigue state, the amplitude and the time of flight images are chosen, and an algorithm is implemented to separate each pixel of each image and downgrade with the appropriate percentage based to the color map to the left, and summarize the values for each case. Afterwards, the damage index is calculated with the equation here down left. RGB color was adopted for the algorithm here, and increase of the damage index corresponds to increase of the delamination area. And MATLAB was used here for the whole implementation. After all this, we come to a point that we have all the pieces and we want to make the puzzle. Aim is to examine if the natural frequencies are decreasing in the same trend as the stiffness does, and to validate this behavior by using some empirical mathematical models from the bibliography. Here are presented two of them. In the diagram left, the residual force function of damage index, both for experimental data and the numerical models, is displayed. The damage indexes are calculated with the equations that are shown here. The experimental one is from the C-scan images and the time of flight images as described earlier, while the numerical one is from the ratio of initial and delaminated nodes to initial nodes. To the right, the normalized ratio from experimental data is presented, as also three empirical mathematical models for eigenvalue 3.5 kHz, which have a good enough convergence. In this slide, two diagrams on the left side show the decreasing trend of two eigenvalues to the normalized fatigue life, both experimentally and numerically. Numerical models have better convergence with expected frequency reduction based on theory due to clear damage mode and separation of each fatigue state from one another. Experimental eigenvalue reduction is observed to be slower and smoother compared to the numerical one. Lastly, the normalized frequency ratio and damage index versus residual fatigue life are presented both experimentally and numerically. The numerical methodology is validated again in coupon scale. Lastly, three main conclusions. These diagrams and their fit curves offer knowledge of residual fatigue life of the coupon through the damage index in correlation with model characteristics, such as frequency here. The linear behavior here depends on the material. the damage evolution and propagation and properties degradation. Experiments were difficult to implement after a certain number of cycles, and that's why the experimental data are less than the numeric. So, as I said in the beginning, the gap of the present literature is the development of a general numerical methodology for prediction the residual fatigue life and strength of thermoplastic composite materials, considering progressive fatigue damage. And exactly this is proposed here, a numerical methodology of residual fatigue life assessment for complex geometries such as aircraft wings or wind turbine blades. Raw measurements will be taken, signal processing algorithms will be extracted, and the examined feature, damage metrics will be estimated, and dynamic behavior of the structure as correlation of residual fatigue life with model characteristics will be known. The exact same procedure can be adopted from aircraft industry using only one sensor. The main conclusions of this presentation are the following. Firstly, a completely and satisfying validation of a numerical-based methodology for estimating the residual fatigue properties. Secondly, numerical models capture the eigenvalues reduction trend and dynamic behavior, which corresponds to the stiffness reduction through fatigue life. And thirdly, the damage indexes, both from experimental and numerical data, were good enough approximations of the quantification of the delamination area. Overall, this methodology could be potentially applied for online monitoring and strength prognosis of vibrating structures, such as aircraft wings or wind turbine blades, provided that vibration signal measurements are available and in the presence of population and operational uncertainty. For future research, work on additional commercial composite materials is proposed, as the adoption of higher complexity methods such as advanced artificial neural network or physics-based machine learning algorithms and compare them with the present results is also suggested. Thank you for your time. Any question is welcome.